the main idea you want to carry away from this is that the cation, which is the positive ion, will always be first in the name and the formula, and then whatever the negative anion will be, that's going to be second in the name and the formula. I always like to tell people to think about sodium chloride, because sodium chloride is always a really good example of all of the rules that we're talking about. All right. IUPAC is the organization that gave us the rules on how to name different compounds. So you will hear us say or ask, what's the IUPAC nomenclature? We're basically saying what are the official rules to follow to name a certain compound. And the word nomenclature means system of naming. All right, so we try to break this up into parts because this can be very confusing because there's different types of things to name. So we'll focus first on writing the formula. And when we say formula, we're talking about that shorthand notation. Instead of calling water water all the time, we can call water H2O. So H2O is the formula for water. Now, first off, if you're writing the formula for a monoatomic ion, mono means one, so we're talking about how do we write the formula for just one element by itself, one ion by itself. For example, you have sodium, which has a +1 charge, and chlorine, which has a -1 charge. So to write the formula for sodium and for chlorine, you're just going to put the symbol. The symbol for sodium is Na, so you just write Na, and the charge of it is +1. The chloride anion is just Cl, and it has a -1 charge, so we put it like that. If you hadn't done so already from section 7.1, you want to go ahead and write the charges for all the common ions on groups 1A all the way through 8A. So everybody in group 1 is +1, everybody in group 2 will be +2 charge, so on and so forth. Now, what if you have to write the name of a monatomic ion? Well, in general, cations, which are usually your metals, they're not going to have any name change. So whatever their name is on the periodic table, that's their same name when they become an ion. Now, if the cation is a transition metal, here's where it can get a little confusing. You're going to write the name as normal, but behind the name, you have to put what's called the oxidation number. And that's how many valence electrons they're going to transfer. Now, the reason being, as we mentioned in the previous video, transition metals can have different numbers of valence electrons at any time. For example, copper can be +1, +2. It just depends on how many it's going to transfer. So to make sure we know which type of copper we're talking about, you're going to put the oxidation number in parentheses. If it's an anion, those negative nonmetals, their last name or their endings will change to IDE. So let's look at some examples. Here is Na+1. Na is sodium on the periodic table. It's a regular metal. No name change, just sodium. That's the sodium ion. Al+3. That's a regular metal as well. Aluminum. So its name will be aluminum. Fe+1. Now Fe, which is iron, is a transition metal. So you cannot just call it iron. You have to put the oxidation number behind the name. So since it says +1, that means this is iron 1 because it's going to transfer 1 electron to be stable. If you see Fe+2, again, that's a transition metal, but this time it's transferring 2 electrons, so we call it iron 2. Here's an anion that's negative, chlorine. It says Cl-1. So chlorine, since it's an anion, we will change the ending of chlorine to chloride. So Cl-1 is called chloride. N-3 nitride. Let's look more about at the transition metals compared to regular metals. So on this large table, you're seeing a mixture of mostly the D block elements, and most of them are your transition or heavy metals. Example, you have scandium right here, Sc with a +3 charge. So we're going to call that scandium 3. Here's another example. You have titanium with a +3 charge right here. So we call that titanium 3. To the left is titanium 2, Ti plus 2. Right here you have Mn, that's manganese with a plus 2 charge, so that's called manganese 2. Here is platinum with a plus 4 charge, that's going to be called platinum 4. Look right next to it, it says Pt plus 2, so what would that be called? Platinum 2. You have aluminum here, and aluminum is not a transition metal, so when you write the name, you're just going to write aluminum. You don't need Roman numerals for that. Now, of course, there are 3 exceptions to the rule for transition metals. Zinc, cadmium, and silver. They are transition metals, but they don't have different states of valence electrons. Zinc will always lose 2. Silver will always lose 1. Cadmium will always lose 2. So if we know that it's always the same thing, we don't have to write the number behind it in parentheses. Zinc would just be called zinc, cadmium will just be called cadmium, and silver will just be silver. Because we all know zinc is plus 2, cadmium is plus 2, and silver is plus 1. Alright, so which of the following is the formula for the ion formed from a beryllium atom? Would the formula for the beryllium cation be Be plus 4, Be plus 2, Be, or Be minus 2? It's going to be B, Be plus 2, because beryllium is in group 2A, and everybody in group 2A will be positively 2 charged. What about Ni plus 3? Would that be called nickelide, nickel 8, nickel 3? Well, nickel is a transition metal, so you don't know what the charge is on it unless we tell you what it is, and we've given it to you there. It's plus 3. That means nickel is losing 3 valence electrons. So the answer is D, nickel 3. Which of the following is the formula for the phosphide anion? P minus 3, P minus 5, P, or P with, this doesn't even look right, Roman numeral 3. Obviously it isn't D. You've never seen anything like that ever, no. Okay, now phosphide, the ending is IDE, that's coming from phosphorus, which is in group 5 on the periodic table. Everybody in group 5 that is a nonmetal will be negatively 3 charged, so the answer, of course, is A, P minus 3. Which of the following is the formula for the sulfide anion? Same thing as the previous question. S minus 2, S minus 6, S, or S positive 2. Since sulfur is in group number 6, it will have a negative 2 charge because it will gain 2 electrons. The answer is A. Now, when it comes to putting these ions together to create an ionic compound, we have to make sure we know how to name that correctly as well. The good thing about it is you're just going to put the names together from the 2 monatomic ions. Now, what we do want to keep in mind is what it says here. Ionic compounds are electrostatically neutral overall. And think about when we did the lab with dry salt. By itself, dry salt does not conduct electricity. Okay? So overall, it will be neutral. There's no charge on that salt. You only got a charge on it when you broke it apart in water. But anyway, for naming though, we have to make sure that the charges will all add up to 0. The total charge of all ions in the formula must equal 0. And also you want to have the lowest ratio of cation to anion. So that means you can reduce, kind of like what you would do with fractions in math class. So let's look at 2 examples. We have sodium chloride here. And we want to know, what is the formula for sodium chloride? Well, most people know already it's NaCl. But do you know why? Why is it not Na2Cl or NaCl3? That's because we first of all want to have all the charges equal up. So what you do is you write down the formula for the sodium ion and the chloride anion. So sodium is Na plus 1. The chloride anion is Cl minus 1. So when you put sodium and chlorine together, the charges should equal 0, and a +1 and a -1 already cancels out to 0. So you just need one of each. So you just put them close together, NaCl. We normally do not write the subscripts of 1, so that's why you don't see Na1Cl1, it's just NaCl. Now what about the second example? Iron 2 oxide. So iron is a heavy metal, once again. The oxidation number is written behind it. So you see iron 2, that means this iron has a +2 charge. So it's Fe +2. Oxygen is -2, so here's O -2. And we know that when we put a +2 and a -2 together straight up, they both cancel out to 0. So you only need one of each, one Fe and one O, to make a very ugly compound. Did anybody catch what I just did there? Determine the formula for the ionic compound formed from potassium and oxygen. So we're going to put potassium and oxygen together here. So first you want to write the symbols or the formulas for each of them. Potassium is K, and K is in the first group, so it has a +1 charge. Oxygen is in the sixth group, it will have a -2 charge. So you need to put a K +1 and an O -2 together. Now, if you add +1 and a -2 together, you'll get a -1 left behind. We have to have it neutral in the end. So that means we're probably going to have 2 potassiums to hook up with the 1 oxygen. Because if you have 2 positive ones, that will cancel out with a -2. So the answer would be K2O. You're going to need 2 potassiums, or 2 of the Ks, and 1 of the O's, K2O. And here's the scratch work to prove that. Another example. What would the formula be for the compound made with aluminum and sulfide? Well, aluminum is Al, and it will have a +3 charge. Sulfide comes from sulfur, which has a -2 charge. So if you add a +3 to a -2, you get a +1 left over. So how can we get enough aluminums to cancel out with sulfur in the lowest amount of each? If you have 2 aluminums, 2 times a +3 gets you a +6. If you have 3 sulfurs, 3 times the -2 gets you a -6. And a +6 and -6 will cancel out. This right here is not correct. That is not the correct scratch work. That's for the previous problem. They got mixed up. Okay, but you can do the work the same. If you have 2 aluminums, 2 times the +3, 3 sulfides, 3 times the -2, so you get positive and -6, which both cancel out to 0. I hate doing things the hard way. I like to go the easy way. There is a shortcut for this, and if you've taken me before, you will remember this. It's called the Criss-Cross Shortcut. So the Criss-Cross Shortcut is the fast and easy way to write formulas, and everyone uses it, everybody, because it's really easy. What you will do first is write the oxidation numbers or the charges on each ion as normal, and then you will crisscross the numbers down to the bottom right side of the opposite ion. And those numbers you're bringing down will become your subscripts. And then you will simplify the subscripts if they have a common multiple. Let's look at an example. What's the formula for magnesium nitride? So here are your options: Mg5N2, Mg2N5, Mg3N2, Mg2N3. Notice that magnesium is written first for all of them, and the nitrogen is written second, because you always put the positive cation first and the negative anion second. So what you want to do for the crisscross method first is write down the ions and the charges. So you have magnesium, so we know that's straight up Mg, which has a +2 charge. And then nitride comes from nitrogen, which has a -3 charge. The Criss-Cross Shortcut says to take the oxidation numbers, or the charges as we call them, and bring them down to the bottom right of the opposite ion. So the +2 on magnesium needs to go to the bottom right of nitrogen. But you're not bringing the positive sign down, you're just bringing down the number 2. For nitrogen, you have a -3 charge. Bring the 3 down to the magnesium. So you have Mg3N2. And a 3 and a 2 does not reduce any, it doesn't reduce any smaller, so it's going to be 3,2. So Mg3N2. Well, let's see. Answer choice C says that there are 3 atoms of magnesium. So you have 3 atoms with a +2 charge on each. So 3 times the +2 is +6. For nitrogen, N2, you got 2 nitrogens or 2 nitrides, and they have a -3 charge each. 2 times -3 is -6. So when you add a positive and a -6, you get a 0. So the answer C is correct. Which of the following is the formula for aluminum nitride? So we're going to do the same process here. So the answer for this one is C, right? Aluminum nitride would be ALN. Why is it ALN? I thought I had it programmed in here. All right. So aluminum is this is about to get real ugly. All right. Aluminum is your cation, and on the periodic table, aluminum is +3. Nitride comes from nitrogen. We'll stick to our regular colors. Hold on. N-3. All right. So you want to take the 3, the positive 3. You're going to bring the 3 down to nitrogen. And then the 3 that's on nitrogen, that charge will come down to aluminum. Right? So you have Al3N3. And as we mentioned before, you want to reduce the subscripts if they can reduce. A 3 and a 3 can both be reduced to a 1 and a 1. So you'll have Al1N1, which is just ALN. Here's another one. What's the name of Li2O? So now we want to write the name of this chemical. Remember, the cations, they do not change their name. So Li, which is lithium, is just going to be called lithium. Anions do change their name. So oxygen will not be called oxygen. In this case, it would be called oxide. So the name of this would be lithium oxide. You just put the names together. That's it. Now, what about this? Cu2O. How would we name this? Well, again, cations do not change their name. So Cu is just copper. But copper is a transition metal. So you have to put its oxidation number in parentheses behind the name. The question is, what is the oxidation number? Is this copper +1, +2, +3, +8, +10? What is it? To figure that out, you are going to basically do the opposite of the crisscross rule. Just uncrisscross the subscripts. So here's Cu2O. The subscript on Cu is the number 2, so you uncrisscross it. So you're going to put the 2 back to where it came from, which is from the oxygen. And we know oxygen is -2, so that works. And then on the oxygen, you do not see a subscript on it. There is an invisible number 1 right there. So go ahead and uncrisscross that invisible number 1, and you put it back on that copper. So it looks like the copper has a +1 charge, and the oxygen does have a -2. And oxygen usually is -2 anyway. So we know that the numbers are true. The answer would be copper 1 oxide. All of these say clicker question number 6. All right, so how about we name this one? Instead of Cu2O, now it says CuO. So we're doing the exact same thing again. The anion copper, its name is not going to change. We just got to figure out what the oxidation number is behind the name. So we're going to uncrisscross again. Now this time you have just a CuO. If you don't see any numbers on the bottom, that means there are it's the number 1 down there. So the Cu has a 1 and the O has a 1 on it. You want to uncrisscross. So bring the 1 from the Cu back up to the top right. So that means O is -1. And then you have your 1 on oxygen. You bring that back up, and there's a +1 on the copper. Now, oxygen, however, is not -1 though. On your periodic table, you should have it listed under the number 2 group. So if oxygen is if oxygen is -2, but uncrisscrossing has it look like it's -1, multiply that -1 times 2. And so you'll have O minus 2 like it should be. However, if you do that to oxygen, you must do the same for copper. Multiply its number times 2, which means copper is going to be +2, so that's copper 2. The oxygen is called oxide, so the answer would be copper 2 oxide. It takes a lot of practice, and you will eventually see the patterns and get the hang of it. So in summary, when it comes to naming ionic compounds, we just have a few rules. It's just a little difficult if you don't know how to distinguish between the different situations. But in general, when you're writing the formula or even the name, the cation will always go first and then the anion. When you're writing the formulas, you have what's called superscripts and you have subscripts. Superscripts are the numbers that go above a symbol. They look like exponents. Superscripts in chemistry represent the oxidation number or the charge. So that's the charge that you will have is the electrical charge from gaining or losing electrons. So you can be +2 or -3 or whatever, okay? That's your superscript. And then the subscripts are the numbers on the bottom. And so that's going to tell you how many ions to have in the formula. When you add up all of the charges from the cations and anions, it should all add up to 0. It must equal 0. Now, lastly, we have something called polyatomic ions. And these are ion groups made up of more than one atom. And when you have them all together, they will have a charge overall, just like the monatomic ions. So here are 2 examples of them. You have what's called the ammonium ion. So you see that the ammonium ion is 1 nitrogen bonded to 4 hydrogens, and it has a +1 charge overall. Phosphate is the group known as PO4. That's 1 phosphorus with 4 oxygens, and overall there's a -3 charge. So that's called the phosphate ion. And there's actually a whole lot more of them. And they all have their own special names, and they have formulas and charges with each of them. You want to treat polyatomic ions just like the monoatomic ions, meaning you're just going to have this one item, and that one item will have a charge. It's just that for the polyatomic ions, they're made up of more than one atom, but you will still treat it like it's just one package, just one thing, and that one thing has a charge on it. We will never change the subscripts in the polyatomic ion, nor do we change the name. What do I mean by this? Well, if you look at ammonium, that's NH4. We'll never change the name ammonium to anything else, and you cannot change the numbers or the charges inside of ammonium. There will always be just 1 nitrogen and 4 hydrogens with that, and all of that added together gives it a positive charge, a +1 charge. Me personally, I don't like how they wrote the charge inside parentheses here. I do believe that when you're writing polyatomic ions, the charges need to be written on the outside. That way you know that the charge applies to everything inside. And the chart that you have is not the complete chart of every single polyatomic ion out there, but these are some of the common ones you'll see in the problems that we'll be doing. What you might want to do is take the time to memorize some of these formulas. And when I was in high school, I used flashcards, but there are online games, quizzes, a lot of things that you can use to help you memorize them. But the best way to memorize them is to just use them. So when we do these practice exercises and you do your homeworks and stuff, you'll be learning them over time. So don't stress yourself out trying to memorize them all straight up. But that is what I did just to make things easier for myself. So how do we use them? Again, you use them just like the monatomics. You're just not going to change the name or what's inside of that group. So here's a question. What is the formula for magnesium nitrate? Well, we know that magnesium is Mg, and Mg has a +2 charge. Now, the second part, the anion here, it does not say nitride. If it said nitride, that meant that it was just an anion, nitrogen, and the ending for nitrogen changed to nitride. But since it says nitrate, that is not the IDE ending. That means this is a special name, comes from a special group, A polyatomic group called nitrate is NO3, and it has a -1 charge overall. So here you're going to see why I like using the parentheses like this. We're going to use the crisscross method like we've done before. So you're going to take the 2 from the +2 and bring that 2 down to the outside of NO3. You're going to take the 1 from the NO3 and bring that down to the Mg. So you'll have Mg1, and then you have NO3, and you're going to have 2 of them. So this is the reason why I like the parentheses, because I don't want someone putting the 2 next to the 3 thinking that you have NO32. That's ridiculous. Okay, so we're just going to use parentheses to separate the 3 from the 2. So the answer choice for this one would be C. Mg parentheses NO3 close parentheses 2. You can check if it's neutral just like we've done before. Mg1 NO32 means you have 1 magnesium. Magnesium has a +2 charge, so 1 times a +2 is +2. And then nitrate, we have 2 groups of it, and they each have a -1 charge, so 2 times a -1 is -2. And of course, a positive and -2 cancel out to make 0. What's the name of Al2SO43? Well, cations, once again, don't change their name. And it's a regular metal too, so we don't have to use parentheses and Roman numerals. This is just aluminum. The SO4 group is a polyatomic ion. It has a -2 charge. It is called sulfate. So the name of this would be aluminum sulfate. That's it. Here's a question asking about calcium and phosphate. So calcium has a +2 charge. Phosphate is -3. It's PO4, which has a -3 charge. So we can use the crisscross method. You're going to bring that +2 down to the outside of phosphate. Bring that 3 down to the outside of calcium. So Ca3, PO4, 2. And you also do want to check to see if you can reduce, and a 3 and a 2 does not reduce. And you can check your charges as well. So we have a couple of summary slides. You can look at this one in your spare time, but the one that I prefer is the naming compounds flowchart, or as I call it, the cheat sheet, because it will ask you a question, and depending on the answer, it will take you through the steps for naming it. So I definitely would be using this. I also have a link to this on the dashboard, as well as handouts that I can give you when we come back from the break. So the front side, this side will help you name everything. The left side is the ionic side, the right side is the covalent side, and that's a whole, the covalent is a whole different set of videos, and it's actually easier, to be honest. But for ionic, focus on the left side. The back side of the handout gives you a list of polyatomic ions. It helps you with some of the Roman numerals, as well as prefixes for covalent stuff, which we'll do later. And then you have some examples you can work on. So I would be working on the quizzes and whatnot online, because you have to practice this to get it. And so in summary, once again, cations first, anions second. If you have a transition metal, put the oxidation number as Roman numerals behind it in the name. Anions change their last name or the last part of their name to IDE. And polyatomic ions, we do not change their name. And there you go.